All right, first off, just a bit of history with regard to magnetism. There are many cultures that have discovered this crazy magical property. In fact, there's a type of stone that can magically attract ferromagnetic material to it. And this type of stone is called lodestone. All right, looks like an ordinary stone, but it is ferromagnetic. All right, and there are cultures that which figured out that if you took this and you suspend it on a string, it'll always orient itself in this dimension, which so happens to be the north-south dimension, and that's how they invented the first compass. All right, so they discovered that Earth has a permanent magnet, and these things like to attract themselves and line themselves up with Earth's magnetic field. Again, text in blue, don't really need to copy down. But what is important is knowing what field lines look like. All right, so here's an ordinary bar magnet, and to the naked eye, we really can't see these fields that come from it. It's kind of like gravity, right? We know that, for example, in my room right over here, gravity has a vector that is pointing downwards. How do we know? Well, I can just take some ordinary objects like these pens over here, and the moment I let go of them, okay, gravity's pointing downwards here. How about over here? Sure. Towards you guys? Okay. I think we got some conclusive results here. We can see that these fields are all pointing downwards, at least in my room right over here. All right. So how would you figure out how the fields behave in a magnet itself? Well, you'll be doing something very similar as well. You need to have some sort of tracer to figure out where the fields are traveling. One thing just to let you know is that there's a term for these fields. Gravity, they're called gravitational fields. Right? These are just lines that point towards the center of the Earth. And magnetic fields exist as well. And they're commonly known as B fields. So let's go and check it out. Let's have an overhead camera view of what's going on. Okay. So here's a lovely bar magnet, and there are fields that come from here, and that's the reason why stuff will want to get stuck to it. All right, but we can't see the field lines right now as is, so we need to include a tracer. And one of the best tracers is this stuff over here. It's nothing more than just sawed up iron, also known as iron filings. There you go. Okay, now whenever you do this demonstration, do not sprinkle the iron filings directly onto the magnet, because if you do, that means that student's going to stay after school and manually pick off every single iron filing until it's all clean. Then that student can go home. Okay, so don't sprinkle it directly on top. Instead, normally I ask students to go and get a piece of paper and drop that paper on top and then sprinkle on top of the paper. To make things a little bit more awesome, what I found was this old Ferrero Rocher container, and it will do the same job, but also be transparent at the same time so that you could see the field lines coming from this bar magnet. All right, so ready for some magic? And yeah, we may as well cue up the music. Here we go. There you go. All right, so what exactly is going on in this crazy looking picture over here? Well, it looks kind of like that, does it not? I know that this one's probably not the best examples, but you get the idea that you'll see that there are these B fields that leave from one magnetic pole and they come back in the other side. So this is a very crude, messy drawing. So to clean it up, normally in textbooks as well as notes, we draw it like this instead. Okay, so copy down the diagram on the right. And while you're copying down the diagram on the right, keep these ideas in mind. All right, first off, these field lines, we can't see it, and they're called B fields. Some textbooks call it magnetic flux density. I'll stick with the easier term. Now, as for standards of convention, when you look at the picture over here, you can't tell which side's north and which side's south, right? They look symmetrical on both sides. In fact, if I didn't color code the magnet, you wouldn't be the wiser. However, we do know that magnetic fields, they do interact with each other such that like poles repel and opposite poles attract. So there must be a direction with regards to these field lines. So the international standard that we go by is that we assume that the B fields leave from the North Pole, cycle all the way around, and return back to the South Pole. That's our international standard. Another rule that which was covered by Mr. Maxwell, he noticed that these B fields always create a complete loop. So in other words, as it leaves from the North Pole, it'll travel all the way around and return back to the South Pole, but inside of the magnet, it'll complete the loop so they can go over and over again. In other words, with regards to the B field, there is no beginning and there is no end. Okay, so once again, when you draw this in your notes, again, make sure that your B fields first leave from the North Pole, travel all the way around, and return back to the South Pole. And you'll draw these arrows to tell the reader that the B fields leave from the North and return back to the South. Internally, if you want to connect it, you're more than welcome to do so because that's what happens inside bar magnets. All right, so the B fields will return from south to north inside the magnet. Okay, so B fields always leave from the North Pole, cycle all the way around, and return back to the South Pole. Make sure that your B fields don't cross. And the reason for that is if you take a look at the picture over here versus what's happening in the field diagram, you'll notice that where all the B fields are closely packed together, that's where the magnetic field strength is the strongest. So as B fields move further apart from each other, the intensity is weaker. And where the B fields are really close together, that's where the magnetic field lengths are the strongest. All right. So if you hypothetically ever had a B field line crossing with another B field line, that means you have a point in space where you have infinite intensity in magnetic field strength. And you can imagine, well, that will happen with that, right? You've turned into magneto, and everything that's magnetic will become attracted to you, even from a million miles away. And that's why we can't have B fields crossing on top, all right? That's one of the reasons. The other reason is that really the picture over here, it's the superposition of all the tiny little magnets inside the big magnet. Okay, well, we'll talk about what that means later on, but we're looking at the big picture, all right? We're looking at the big picture, and in the big picture, we can't have B fields crossing on top because it's mathematically not possible. In fact, if they were technically on top of each other, then we just simply as a vector has a bigger value because it's the summation of the two smaller vectors. Okay, so we'll never have B fields cross, ever. Okay, so that's of just one lonely magnet. But what happens when we have more magnets with each other? All right, such as the case where you have, similar poles with each other, and what if we have opposite poles with each other? And yeah, we'll do another live demonstration with that. There you go on full screen. Okay, look how strong these magnets are. They really hate each other. Oh yeah, that's beautiful. All right, but I don't want them to completely repel from each other. I just want to set it up, and then I just want to see the corresponding field diagram from that setup. Ooh, it's turning. Stop turning. Okay, let's check this out. Do I really need the music? Well, how about the other music? Let's see what happens in the middle. As I shake, 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 yeah, we'll see field lines over here. That's beautiful. On the far end, we'll see other field lines. But what happens in the middle between these two? Huh, you'll notice that there are no field lines in the middle, right? There's no iron filings attracted to over there. So that's something to keep in mind when you draw this type of diagram. In fact, let me just switch back. And you can see that in the diagram, it's exactly what happens. So again, just be very careful in your drawings. Make sure that your B fields do not cross. Because again, if they cross, that means you have a point where, mathematically speaking, it has infinite magnetic field intensity. But what you will notice in your drawings is that in the complete center, you won't see any magnetic field lines at all. Okay, now let's set up the other case now, okay? And I'm going to try to set it up so that's in the same orientation as in the setup. So it'll look like that, yeah, as in the PowerPoint. Now you'll notice if I place them too close to each other, they're going to attract. So I need to keep them far away enough that they don't stick. So some distance like that, but close enough together because I want you to see what happens directly between these two. All right, so pretty much the same exact setup. And let's check out the outcome. Cue the music, because we love cueing out the music. Oh yeah, disco, disco, disco. Sure, I can zoom in just by a slight bit just so that you guys can take a look at it. Okay, now I gone a little bit overboard over here, but I hope you get the idea right in the center. What you can see is that the magnetic field intensity is much stronger right between these two. All right, so they're going to attract far more iron filings than they normally would by themselves. Okay, just like in the diagram over here. As I briefly mentioned, what you're seeing really right here is the superposition of the two magnetic fields. All right, because we know that from the North Pole, for example, we have B fields that are leaving from it, and I'll just color it in red. Where's red? Here you go. Okay, so if B fields leaving from it, that which looks something like this. All right, and we know that there are B fields through the middle. But on the right-hand side, we also have B fields that travel in the opposite direction. And if these are two identical magnets, it's of the same intensity. Okay. Now, here's the thing. When you take a look at what's happening in the middle, if you treat B fields as a vector, which is what they are, here's the North Pole coming from the left-hand side, and here's the North Pole coming from the right-hand side. If they're equal in opposite intensity, when you add them together, right, so that vector plus that vector, you end up getting what?
0.
Exactly. You get 0. All right, so they mathematically have subtracted or differenced themselves out or canceled themselves out, if you want to describe it that way. And that's the reason why you'll see no B fields in the middle. Again, it's not that they've disappeared. You're just looking at the final outcome of the interactions of these two magnets, where they net to a value of 0 in the center. And if you take a look at the example over here, we have double power, because coming from the right-hand side, we have B fields moving towards the left. And as you know, with magnetic south, the B fields return back to the left from the south pole. All right, so with the south pole, B fields returning back. We have B fields leaving from the north pole. So when we take a look at the mathematical sum, if one of them is pointing to the left and the other one's pointing to the left, you get double the intensity pointing to the left. And that's why the magnetic field intensity is so strong between these two opposing magnets, which as a result causes them to want to attract one another. And we end up with these diagrams here. There's this theory, and it's called the domain theory. And as I mentioned with regards to theories, it's a way of explaining how the world works. And it's okay until somebody else says, wait a second, it doesn't cover this. And then they end up making a new theory afterwards. It somewhat did happen with the domain theory, but the interesting thing is that domain theory, it still exists to this day. So we'll still use this to explain the general basics of how magnetism works, because it's a great way to introduce the whole idea behind it. And domain theory simply states that any magnet you have around is really made up of teeny tiny little magnets inside. Okay, and those teeny tiny little magnets, they're called either dipoles or dipole moments, depending on the textbook you read them from. All right, so every big magnet is made up of tiny little magnets. So you could have metal that has not been magnetized yet, kind of like these paper clips over here. All right, these paper clips, they do not want to stick with each other whatsoever. All right. But if I'm able to line up all of their little magnetic domains or their dipole moments, then yes, it can become magnetized or temporarily magnetized. Okay, so if all the little magnets that make up this big magnet over here are all lined up like in the picture over here, this will become a magnet. Best way to demonstrate that is to take my really strong magnet, place it on top of this paper clip over here, and with that, what am I going to dare myself in doing? I will do it the safer way, because I don't want to dirty up this magnet here. Okay, so I have this, and with that set up here, just so that you can see it in space, here are my iron filings, and here they are all attracted to it. Okay, and if I take away the strong magnet from it, it will temporarily stick for the first moment, because their moments are still aligned with each other. Okay, so there's still a little bit of alignment because they're all in close vicinity. However, because I haven't tempered this properly, the domains will become random the moment I drop it, and you'll see it's lost its ability to magnetize afterwards. Okay, so if you want to magnetize something, especially if it's of some sort of soft iron, it has the ability to become permanently aligned. And what you need to do is you need to take a permanent magnet and you need to swipe it across that temporary magnet enough times. And as long as the metal has been properly tempered, eventually the field lines will all just line up and it'll become a permanent magnet. And that's what I do with these magnets over here. All right, I put it in a very strong magnetic field. Then one side has B fields leaving from it, and the other side has B fields that return back to it, making magnetic north and the return back of magnetic south. So as long as you swipe a permanent magnet through anything that's ferromagnetic, eventually it'll become magnetized when all the domains are all lined up. As what the video has mentioned, only certain elements exhibit this magnetic property, and the three major ones are iron, nickel, and cobalt. Hans Christian Oersted noticed that if you allow current, for example, to travel towards the left, you start using your right hand rule, so physically your right hand, and you let your thumb point in the direction of current flow. And if the current flows this way, in other words, I had it hooked up in this manner, so positive goes over here, and the positive field, the positive current's able to flow through the wire through here, all the way around. Then at this top part here, the current will be flowing towards the left, and I use my hands to tell the reader that at the top of this wire, the B fields will be traveling upwards. Okay, and if I'm beneath the wire, the B fields will be traveling downwards. And that's because B fields will always create these circles around the wire, like so. So you'll have one B field ring inside here, another B field ring over here, another B field ring further out here, and another one even further out. So these B field lines that are created, they are not in alignment with the wire. Instead, you'll notice that they're always going to be 90 degrees to it, this way and this way. In other words, it'll create concentric circles that are orthogonal around a conductor. So these pictures are all based upon something called the right-hand rule. And if you take a look on this history timeline, I hope it doesn't block off too much of your text, but Oersted's principle was back here in 1820. All right. This is well before J.G. Thomson's plum pudding example, which described that atoms are made up of protons and electrons, which was discovered almost 100 years later, like 80 years later or so. All right. So as I mentioned, a lot of things that we do in science is because it became a standard due to a theory from back in the past. All right. So until 1897, we've been assuming that current has been flowing from positive to negative. So in this unit, we're just going to continue with that wrong theory. Because you got to keep in mind that the whole understanding of volts, amperes, ohms, Kirchhoff's laws, and even Thomas Edison and Nikola Tesla, they all assumed that current flowed from positive and negative. And it wasn't until about 100 years ago that they disproved that. All right, so are we going to go off and delete all of that old history? Probably not, because again, they had positive, conclusive results, and they were true each and every single time. And that's why those laws or those formulas are still valid to this day. All right. So to keep with that trend, since all the research was done back 200-300 years ago, we'll still assume that current goes from positive to negative, even though it's disproven otherwise. But I was at a science center out in the West Coast, and they had a very similar setup, except they didn't want you to play with iron filings. Instead, they placed tiny little magnetic compasses all around the conductor. So let's play that video and see what the outcome is. That's my hand. And there's the clunk. You guys see that? Isn't that beautiful? So here's a snapshot of that frame over there. And you can see that, yes, all of the little compasses, they're all in alignment with each other. They should be facing the same direction. However, some of them, unfortunately, again, they got messed up because thousands of kids are playing with it. So they're not perfectly pointing that way. But you can still see these concentric circles. Then we can do the reverse right-hand rule, where our fingers indicate the direction of B fields. So if you look at this is you're looking at it from slightly overhead, you can see that the B fields are kind of curling like this. And your thumb points to where the current is flowing. So in this setup over here, we can assume that the current is flowing upwards. Okay, so it's coming from somewhere down underneath the table, traveling inwards, traveling upwards, and these are the concentric circles that are formed, and they're all traveling counterclockwise from this perspective. Okay, so here's the symbolic notation to describe fields or vectors that are pointing either out of the page or into the page. And we go by this dot X notation, where dot indicates that the force, the field, or the current is pointing out of the page, like right towards you guys. So the first case over here, that blue circle in the middle, that indicates the fact that you're looking at a conductor straight on like this. Okay, and the dot is just reminding you that the current in the setup over here is pointing towards you, the viewer. So it's coming towards you. You can see that the B fields are circling towards the left at the top and towards the right down below. All right. So when you label this, you're going to go off and draw these little chevrons, these tiny little arrows, and that's to tell the reader which way the B fields are traveling. So just draw, a handful of them, anywhere from, 6 to 12 of them, and that's more than enough to tell the reader what it is. The last thing you want to do is remind the reader that those are the B fields. So let's try out the next one. Okay, what is the answer for the next one? Well, right now we can't tell if the current is coming towards you guys or away from you. But what you do know is if you place your hand on top of the screen right here, you can see that your fingers kind of look like this, at least from my perspective. And then from your perspective, it's going to look like that. Yeah. So that's what you're going to see, right? You're going to see that the B fields are going to the right on top. They're traveling downwards on the right-hand side. They're traveling to the left at the bottom, and they're traveling upwards on the left-hand side. And in this entire rotation like this, your thumb is constantly pointing into the piece of paper or into the wall. Okay, so to tell the reader that the current is going into the wall, again, the memory aid for this is look at an arrow. If the arrow is going into the wall, then all you see is the X. All right, so the correct answer for this one over here is X, to tell the reader that X marks the spot. You're going into the page. It does help if you have some sort of, object around, even if it's your pen. Your pen will work just fine. I'll just use this because it's nice and big. So the current is going down the page. All right. And according to your hand over here, you can see that according to the diagram, the current is moving to the left, at least in front of this orbital path that it looks like. Okay. So it's traveling towards the left. So that's why I have my chevrons pointing to the left. And then they'll be traveling towards the right through the back. So I'll include some arrows behind to tell the reader that the B field lines are traveling out through the back. And that's how you would answer this question here. You just draw that out, and then you'd label to the reader, telling them this is the direction of the B fields. there is a mathematical equation in predicting the magnetic field intensity through a piece of wire. And the formula looks something like this. B is equal to mu naught times I over 2 pi r. As for the derivation of this, it's beyond the scope of this course, so you don't need to worry about that. And in fact, this slide you don't need to copy down. But what I do want you to know is what the relationship is in our setup. Okay, so this formula will be given to you just as a reference, but you're not going to do any calculations with it. First off, if you're wondering what these units all mean, mu naught is a constant. It's known as the permeability of free space. It's a constant of 4 pi times 10 to the negative 7 Teslas times meters per ampere. We'll cover that in grade 12, right? Just know that it's a constant. It's just a fixed value. I is the current that's passing through the conductor, and it's divided by 2 pi r. Okay, so from looking at this formula over here, I hope you can see the relationship between B and I. Right? What is that correlation? What's the relationship between B and I? You'll notice that if I doubles, B will definitely double when you sub the values in. So in other words, they're directly proportionate. All right, so you double the current, you'll double the B field intensity. And it's inversely correlated with another thing, which is R. And R is the radial distance away from the conductor. So however many meters you are from the conductor itself. Okay, because the further away you are, the weaker the magnetic field strength. And you're probably used to that with permanent magnets. All right, and the same thing happens with this conductor here. The magnetic field intensity is very strong near the conductor, but it becomes quite weak on the far end. And when you look at this formula over here, B and R, they are inversely proportionate with each other. So that's all you really need to know about this formula over here. Now, that's with a straight conductor. And as I said, with a straight conductor, the B fields emanate around the conductor. And yeah, it's going to be very weak. It's not going to be all that exciting. All right. So to make it more interesting, why not just take the straight conductor and start looping it around like so? And let's analyze in this picture what's going on. All right. So we have a loop that looks something kind of like this floating in space right now. And if you observe the current is coming in from one end. I'm trying to simulate what it looks like on your screen. So what am I supposed to do? So hold it like this and hold it like this for you guys. Yeah. All right. And the current is going in through the back. And as it goes through the back, you can see that if you use your right-hand rule, the B fields go up through the middle of this curl. Okay. In fact, over here, the B fields still go up. And when my current's going this way, my B fields are still going up. So the entire journey of that current as it's cycling through, you can see the B fields are continuously pointing upwards, like in the diagram. And then that starts resembling something that we've seen before. Doesn't this look kind of like this? Okay. So that's the cool thing about this setup over here. It starts to resemble this picture over here. And that's just with one loop. Well, take that idea now, okay? You have one loop, and your one loop is forcing all your B fields all together, so it's all behaving as magnetic north over here and returning all back as magnetic south. What would happen to the setup if I decided to flip another loop around? What will happen to the intensity? Double, good. And if I flipped another loop around here in the same setup, the intensity will triple, good. And that, my friends, is the introduction towards what a solenoid is. A solenoid is nothing more than just a piece of wire wound it around plenty of times, and you created a solenoid. Solenoids are effective at creating a very strong magnetic north domain and a very strong magnetic south domain, or pole, sorry, in a setup in space that's temporary. All right, it's not permanent, right? So I'm going to switch over to camera view of a solenoid. Now, it's not going to look exactly like this because it's all compacted together. Instead, I'm going to spread it out, make it nice and big. It won't be as strong or as effective, but it'll get the general idea across. So here is my three-dimensional solenoid, and you can see that the coilings go through this plexiglass over here. That way we can see how the B fields look like, at least when we take a little slice from the center over here. So I'm going to sprinkle some iron filings on top, and I'm going to see if there's any resemblance of any sort of pattern with the setup. Okay. Now, again, electricity is colorblind. It doesn't care what color the wire is, but just to keep to a standard convention, we always like to use red as our positive and our black as our negative. Again, back 300 years ago, they had no idea which way current flowed from. Was it from here to here, or was it from here to here? So they just made an assumption and assumed that current flowed from red to black, or from positive to negative, because they observed the same exact outcome as our setup over here, and it can be used to predict the direction of the magnetic field. And here's my compass to show it. Hey, why aren't you lighting up? It's because I didn't plug it in properly. Because if I did, you'll see sparky spark. Look at that. Okay. I'm using an insane amount of current just to do this demonstration. So it will smoke up and it will stink. And two things you'll notice. First off, you'll see that this is pointing towards it. And number two, if you look really closely, you'll start to see that there are lines in the center. Yeah, this crazy thing does happen, all right? That when you pass current through a solenoid, you will force all the B fields to all congregate together and separate on the other side. Now, here's the question. Does it come in like this or does it come in like that? And really, we can't tell. The only way that I can really tell is by taking each and every single one of these iron filings and coloring one side red and one side blue and then putting them all in here so that if we zoom in enough, we can start seeing it. And that's difficult. We're not going to do that, okay? And that's why I had this little tracer over here. And if you notice, this started pointing this way. And so if it points this way, then it's telling us that this side must be magnetic south, all right? So this side over here is magnetic south, and on the far end, it is magnetic north. So we have south on this end because the north pole pointed towards it, and logic dictates that this side over here is north. So what's really happening is that the B fields are leaving from the top and returning back to the bottom and cycling over and over and over again. So let's go in and try to prove that, yes, it's going to be south on this side and north on the opposite end. So here's a picture of what happened, and I guess it's flipped the other way around. Oopsie daisy. Okay, because again, if you look at my video setup, you can see that I had my red on the bottom and my black on top. So really in this thing over here, it's just the other way around. Yeah, so really it's just taking this and flipping it that away. Oopsie daisy, I should have paid attention to that first. But this is the outcome you would have seen anyways. Okay, if you flip it around like this, you'll see that the compass will flip this way because north loves south. All right, and that's what would have happened in the setup. So again, we have our current flowing from the top up here, okay, because again, that's where the positive lead is. And as the positive lead comes down, we have our current sticking out through the right-hand side. So it comes out on the right-hand side, travels up and down on the left, like so. Then I'll go down through the plexiglass, go up all the way around again, and become a dot yet again. So we have X's all on the left, and we have dots on the right, like so. Now I'm just going to remove the background so we can see that this is what we're up against. Okay, and then I'll bring that picture back so you can prove to you why it is what it is. Okay, now there's just too many X's and dots here. I could draw them out, but it'll just take too long. So I'm just going to skip to every second one. That's all. Okay, and again, I'm only skipping just for time efficiency. You could go off and draw all the circles for this and come to the same conclusion. All right. So with regards to the X's on the left-hand side, we're going to use right-hand rule number 1 again, or Oersted's principle. X means that you're going to stick your thumb right into the page, or in my perspective, I'm pointing it this way. And then when I'm drawing it, I'm going to see that I have B fields that are going to circle around clockwise, like so. Now, in the interactions between the middles of these two, you'll see that the B fields are going against each other. Okay, so what ends up happening is that really, when you look at the end of what's happening in the middle, they get canceled out. So the smaller circles, which I'm going to start off with, I should have started with smaller circles. Okay, the smaller circles, they're still abiding by this right-hand rule number 1, where the B fields are traveling, at least from our perspective, clockwise. But the mathematical outcome of the next ring is that they will cancel each other out, as I explained. Because again, you have a B field that's traveling towards the right, and you have another B field traveling towards the F, and what we're looking at is the outcome of it. I'm sprinkling the iron filings on top, and right and left will cancel each other out. So what we end up having is something that looks kind of like this. And just follow along with me here. Some people are wondering, should I copy this down? I'll leave that up to you, but I just want you to see the overall picture, because this is more of an understanding of why does right-hand rule number 2 work. I'm getting to right-hand rule number 2. Okay. Again, mathematically speaking, those start canceling each other out, where at the end of the day, you're going to see this really long, elongated oval. In fact, I'm going to stop there. I think that's enough there. Okay. Now I'm going to rinse and repeat on the other side, and I'll color code it differently just so that you can see that I'm doing the other side. Okay. So this time around, there's a dot. So the dot's going right to your eyes, and as a result, the B fields will curl like this. So it's going to curl counterclockwise. I'll start with the smaller one. Okay. So counterclockwise, all of them will. And the interesting thing is the next ring. Okay. In the next ring, again, they're going to mathematically cancel each other out right at the intersection there because they're opposing in direction. So our next ring will start looking kind of like this. And it's just going to keep on averaging itself out to start looking like this. In fact, this looks just like that, doesn't it? Okay. And in fact, as we described, the B fields, they leave from the North Pole and they return back to the South Pole. And as predicted, that is the outcome from our setup. There you go. There's the proof. Okay. Now, the proof that I'm doing here, you can see that it took quite a while, right? I spent probably 2 to 3 minutes trying to prove that this side here will be north down below, and up above, it will be magnetic south. But there is a much faster way of getting to the answer, and it only takes about 3 seconds. And that is right-hand rule number 2. Right-hand rule number 2 states this. Take your lovely little fingers. Your fingers will indicate the direction of current that's flowing through the conductor right over here. So in this setup over here, if this is the positive end, we're going to have our fingers go up through the front, like so. So as the fingers go up through the front, our thumb goes, good job, North Pole. And if you look at the setup that we have here in the video, it's exactly the same as our outcome. Positive on top, negative down below, our thumb points downwards, telling us that North Pole is at the bottom. Right-hand rule number 2, and you'll see it written on the next PowerPoint slide, is that your fingers indicate the direction of current flow. So if this is positive over here, it's going to flow this way out through the front. So that's why my fingers are going to point to the front. And as they point downwards to the front, they go upwards to the back and eventually exit out on the negative end. And in doing so, in this setup over here, my thumb always goes and points to, good job, North Pole. Okay, so that's why North Pole points out over here. So according to the setup that I had over here, we had it set up like this. So if I rewind back, there you go. Positives on top, negatives down below, and this is pointing down below. Now, guys, just watch out. Don't assume that the minus sign and north are pointing in the same direction. Okay, a lot of people think that that's the case, but that's not always the case. That's just the setup based upon how I have it set up over here. Best way of drawing it is you'll have this thing which represents your solenoid or your tube. And you can see that right here, you start from the left-hand side and going up and around. So that's what you're going to draw. You're going to draw a little fish hook that looks like that. And then from there, you're going to try to imaginarily extend that where that end of the fish hook is, and then continue on with these letter S's afterwards. All right, so this is Art Class 101 with Mr. Nee, and that's how you draw it. So in the first diagram, we see that current is going up through the front. So then you can start placing your hand on top of these solenoids, right, where your fingers point in the direction of current flow. So it's going up through the front and down through the back, like so. Okay. And as you have your fingers going up through the front and down through the back, look at where your thumb is pointing. And you'll see that your finger is pointing to, good job, North Pole. So on the left-hand side, it'll be magnetic north, and on the right-hand side, logically, it'll be magnetic south. And yeah, maybe it is nice to have some paper toilet rolls around. If your current is pointing upwards, you take your hand and you allow your hand to point upwards through the front of the tube. And that tells us that to the left is where magnetic north is. So that's why north is on the left-hand side and south is logically on the right-hand side. In the second example, this time around, we have north pointing towards the right. And with north pointing towards the right, you can see that your fingers are now pointing downwards through the front of the solenoid. Yeah, it's going up through the back, but it's going down through the front. All right, so at the front, you'll be drawing all these down arrows. And if you follow the path of this treasure trail, it'll tell you that the current exits on the left-hand side and enters in from the right-hand side. Okay, so the answer key is based upon at least one of the givens. So between these two diagrams over here, they do look almost the same, right? In fact, they are arguably speaking the same solenoid, right? The setup is exactly the same. But you'll notice that the moment I change the direction of current flow, right? Because if you look at the example on the left, current enters in from the left-hand side, and the example on the right, the current's entering on from the right-hand side. Just by doing that, we have affected the directions of the poles. You can see that they're facing the opposite way. All right, so by just flipping the current around, you will be affecting which side is north and which side is south. In the third example, the diagram looks very similar, but however, if you look at the direction of coiling, now it's entering in from the back and exiting out through the front. Okay, when you look at it from left to right. So it's coiled the opposite way around. In other words, the outcome of this setup or this experiment will give you the complete opposite answer. All right, so south is still on the left-hand side, north is still on the right-hand side, You take your toilet paper roll, hold your hand as necessary, and this time around, yes, the current is going down through the front. So we have arrows pointing down through the front. However, this time around, it exits out on the right-hand side. So you'll notice that even though the poles of this example here in the middle versus the example on the right, the poles are still pointing the same way, the current now is the opposite way, and that's because the direction of coiling has changed. You double the current, the B field intensity will double. You double the turns, the B field intensity will increase. You let it be all loosey-goosey like this diagram or the setup over here, and it won't work as well. If you really want it to work really well, try to squish it as close as possible together. All right, kind of like my solenoid right over here. Right, it's not the best of examples, but I did try squishing it together. In fact, to make it even closer together, you want to lose the jacket. All right, with this wire over here, this is a copper wire. There's a jacket that's probably the same thickness as the wire itself. So if you look at this wire over here, you can see that the jacket is relatively thick compared to the wire itself. You want to try to minimize it by using this special type of wire called insulated copper wire. All right, here's the part that's already been scraped off. I don't have an X-Acto knife with me, but with the X-Acto knife, I can just scrape off all of the oxidized layer, and you'll see that there's some shiny copper right there. And the jacket is not much thicker. All right, this is called insulated copper wire. Some people call it quote-unquote magnet wire, but trust me, this is not magnet wire. A magnet is not attracted to copper whatsoever. Okay, it won't stick to the magnet. Okay, so it's just copper wire that has a very thin jacket, kind of like if you have nail polish on your fingernails. Instead, they use that same nail polish called an enamel, and they coat this with that enamel, right? So it's an insulator. That way, you can pack it as close as possible. So yes, this is a much more efficient solenoid than this example here, which is much more efficient than this guy over here. Now, to describe that last concept, as the permeability of the core material increases, the B field intensity increases. That's why I want to show you this last demonstration. All right, so right over here, I have a solenoid, but if you look through the solenoid, it's just a completely empty tube. That's it. Okay, so you can see that it's an air core in here. And air is one of the worst cores that you can use as a solenoid. I mean, there's stuff worse than that, but it's pretty bad. All right, it's as bad as free space. In other words, if you go into outer space and you have no air particles in there, it's about as bad. All right, so it's not going to work very well as a solenoid. So I have it plugged in to the DC common, and I have it hooked up to 12 volts / 6 volts DC. And right now it's at 6 volts DC, 10 amperes, because again, it's current that dictates whether this will work or not the voltage. Okay. Now it is proportional to voltage because this wire here has a resistance. So if I double the voltage, then the current will double. That is true. All right. But then it'll get twice as hot faster. So that's why I want to keep, I want to limit things. Okay. I don't want this to overheat because it does hurt the fingers. Okay. And yeah, I'll need a tracer. So welcome back to the iron filings. Okay, and again, with regards to this screwdriver I have over here, it's completely demagnetized. You can see that the iron filings are not attracted to it whatsoever. Okay, no magic tricks over here. Here I have a solenoid where the moment I turn it on, it will cause the iron filings to become attracted to it. Okay, so here we go. I turn it on, cue the music in your head, and there you go. And then I'll play the Oh No song because look at that. Barely any was attracted. In fact, there's the comparison. That's all I picked up. As I said, the core that I chose here is air. Air is a terrible core to use for a solenoid. If we want it to be better, we want to choose a core where its magnetic permeability is a lot more than air. If you recall in the previous slide, this will improve it by at least 200 times as it is iron-based. Okay, so let's go and see it improve by 200 times. And you can cue the astronaut song in your head to avoid any copyright infringement. And here we go. And here's the magic. There you go. Pretty neat, isn't it? Okay, and yes, it's going to retain some of that magnetic field because this screwdriver can become magnetized. So effectively, it's the first diagram plus the second diagram equals the third diagram. All right, so let's describe what's happening right here. Okay, first off, the uniform field is one from a magnetic field source where, again, B fields go from north and they head all the way to south. That's what happens with magnetic fields. With a straight conductor, things do get rather weird because with a straight conductor, there is no actual magnetic north and no definable magnetic south. All right, north and south is all relative to where you are positioned to the conductor. So in other words, if I'm standing over here and we know that current is going up, then from the perspective over here, magnetic north will be closer to me and magnetic south will be closer to you. However, if I look on this side of that conductor, Now magnetic south north is closer to you and magnetic south is closer to me. So it does change in definition depending upon where you're standing relative to the conductor. Okay, so yeah, let's describe the one that's in the diagram over here. I think we see a letter X. Yeah, so X means that the current is going into the page. All right, so in your imagination, you're putting your thumb into the piece of paper. All right, and as you place it into the piece of paper, you'll see that the current, or the B field, sorry, start to rotate clockwise. Yeah, clockwise from your perspective over there. Again, the definition of north and south changes because, for example, if you're looking at it from right over here, then north will be here and south will be here. Meanwhile, if you're looking at it on the other end of the piece of wire, then north will be up here and south will be over there. And that's what's happening in the setup over here. We're superimposing these two on top of each other, north and south. All right, so now let's have the pictures superimposed with each other. So I'm going to represent that straight conductor. Again, that's going into the page. So it's from your nose into the page. And from it, again, the definitions of north and south are different depending upon where you're staring at it. Because if you're staring at it on the left-hand side, it looks like that. Okay. And if you're staring on the right-hand side, then you have south over here and you have north over there. And again, you're relating this north and south with regards to these green lines here. So according to this green line here, again, north would be all the way over here and south would be here. So as a result, at this point at least, you'll see that they hate each other and they're going to move apart from each other. On the far end, let me just redraw my north from the field and south from the field. You can see that this time around, these foot poles are opposite to each other. And as they're opposite, they're going to go and attract towards each other. So as a result, this conductor will be pulled towards the right. If you need me to draw this slightly larger, sure, I can explain this one more time with a larger diagram. Okay, so here are my uniform B fields, where again, north is all the way down here and south is all the way up here. And that's true for each of these arrows. So all these arrows exhibit, south on top. It's also south over here as well, just FYI, and north over here. And it's still going to be north, at least relative to that point in space. Okay, so it's north and south is all relative depending upon where you're standing. And since the conductor is just standing right over here, it's going to generate its own magnetic fields. X means that it's going to have fields that are going to rotate like so. All right. So as a result, it's going to have a north over here and it's going to have a south over here. And hopefully you can see that the south does not like the south from the permanent magnet, and the north from the conductor does not like the north from the permanent magnetic field. All right. And on the right-hand side, the opposite happens. All right. Because on the opposite side, again, as the current's flowing downwards, we have, where is it? North on top and south, but down below. All right, so the south down below likes the north of the permanent magnet, and that's why I should draw this in a different color. That's all, just to avoid all the confusion, all this stuff over here. So that's pushing that way, that's pushing that way. This is attracted, so it's pushing this way, and that's being attracted, and it's pushing that way. Okay, so as you can see from all these perspectives over here, they're all resulting in the same consequence. This conductor wants to move towards the right. And this force to make it want to move towards the right, this is technically known as the magnetic force, so FMAG. Now, the explanation of what's happening over here, it does take a lot of steps in getting to it, and eventually we will get to the shortcut. But before I get to the shortcut, I really want to prove to you that all this crazy stuff, it does happen. Okay, so the first thing I'm going to demonstrate for you guys is, how in the world do we create this whole uniform magnetic field? Okay, where does a situation like this come from? Well, that's why I have a horseshoe magnet around. So let's go and see what the field lines look like in a horseshoe magnet. So cue the music, and here we go. Hope you guys can see what just happened here, right? If I move this tray out of the way, look at that. We do have parallel lines. Okay, so it is possible to create a circumstance where you have parallel B fields, and that exists with all horseshoe magnets. Remember, in a horseshoe magnet, you have magnetic north over here and you have magnetic south over here, and really, even though that they may be opposite ends of the pole, they find that the closest path to get to each other is directly across, and that's why you're going to see parallel B fields over here. Also, they mathematically work out that way as well. Next, we need to have a straight conductor that's going to pass through. And that's why on the left of it, I have this crazy setup over here where this wire is able to freely move to the left and to the right because I can't float things here. Unfortunately, there's gravity, which will cause the wire to sink. So this crazy lever system will allow it just to float there so that it'll either be attracted to the magnet or repelled from the magnet over here. Now, I want to simulate the same thing that's listed in your notes. So it's showing me that the B fields need to point upwards. Again, B fields go from north to south. So I need to take the setup and I need to flip it around, right? So that my B fields go from north to south. Next, in the setup over here, it shows that X means that the current is coming towards me, okay? And that means that I need to have positive coming from your side and negative coming to my side, right? I don't know if you can see the colors, but here's the red wire, and trust me, it's connected to the red side of my power supply, all right? So my current leaving from my power supply, traveling all the way across, all the way down the wire, and then it's pointing towards me. So we have the current going towards me. We have our magnetic field. It's going to be placed just like this. And in our predictions, it says that there's going to be a magnetic force acting on the wire, causing the wire to move towards the right. Ready to see that demo, guys? And whatever with copyright infringement. Let's go play the song anyways. Ready? Cue the music. What you know about rolling down in the deep when your brain goes numb? You can call it. Things don't always work out as you would hope it to be, but that's why you persevere and you try and try again. So if it doesn't work the first time, figure out what's wrong, and then hopefully the second time round, cue the music, and there you go. All right. You can see that the wire is being pushed towards the right. That is the magnetic force, and it does happen. Yeah, wow, it does happen. There you go. Okay, back to the screen now, because again, this explanation over here, it's telling you the science of how it works, but that's a lot of steps. So how about we talk about how to solve this problem in less steps? And that trick is known as right-hand rule number 3, also known as the motor rule, all right, depending on textbook you read it by. And here's how the shortcut works. First off, use your thumb to describe the direction of current flow. So in this setup over here, again, the current is moving away from the camera and towards me. That's why the thumb is pointing this way. Next, your lovely fingers over here, you need to orient from magnetic north to magnetic south. Remember, your fingers point towards the south pole. So that's why I have it all set up like this. All right, so as long as the current is going towards me right now, and as long as the B fields are going upwards, you'll see my hand is the direction of the push. All right, so that's why the wire got pushed towards the right. Now, other teachers, they'll show it a different way, and they'll hold it this way, and that's perfectly fine as well. All right, so if you want to hold it this way, by all means, okay? The thumb is the direction of current flow. Your finger points into the magnetic field lines, and then your finger that's tilted at 90 degrees, like so, this is telling you the third resulting force, all right? And the force, in this case over here, is pointing this way, where from your frame of reference, at least, it's moving towards the right. Again, your thumb points in the direction of current flow, so you'll list it with the letter I. Now, technically, current is a scalar vector, but I think in your textbook, it just calls it I with an arrow on top, just to tell you that even though current's a scalar quantity, we're still giving it a direction in the setup over here. So the current is pointing, again, towards wherever your thumb is pointing, all right? Your fingers always point from magnetic north to magnetic south. So north is on this side, and south is on the far end. Lastly, your palm points in the direction of the magnetic force. So the resulting force, in this case over here, gets pushed upwards. There you go. All right. So these problems over here, they're always going to be three-dimensional, and that's the reality. That's why your hands are always held in this weird, funky fashion. Again, this C shape over here represents a permanent magnet like this guy over here. All right. So magnetic north is on top, magnetic south is down below. And again, the B fields always go from north pole to south pole in this fashion. Now, the question is, which way will this conductor move, at least in this setup over here? So go ahead, take your hands out and follow along. Okay, so we're going to assume current flow. Current goes from positive to negative. That's why we're using a right-hand rule. So the current is coming this way. Our B fields are going from north to south, and as a result, the conductor should push this way. All right, so I'm going to take my conductor. I'm going to place it like this to match it up with the picture. No, wait, you guys will see it like, how will you guys see it? Oh, no, I just want to show it the same way you guys will see it. I think you guys will see it like that. All right, so what you'll notice is that once I turn on the current over here, the wire will get sucked into the permanent magnet. So shall I cue the music again? The original audio track. There you go. Here's an original recording just by me. And hopefully it plays properly this time. What you know about rolling down in the deep when your brain goes numb? You can call that mental freeze. When these people talk too much, put that stuff in slow motion, yeah. In slow motion, yeah. There you go. All right. Science does work out. It does. All right. So in your notes, what you would state is that in this case over here, you'll have an arrow pointing this way, and that describes the magnetic force. The magnetic force will be pointing towards the left. Before I move on, one of the questions from the homework, I just want to revisit this one from a different perspective. Okay. And to solve this using right-hand rule number 3, what you want to do is that you want one of these conductors to be mobile and able to move, and the second one just to be a fixed object, creating its own magnetic field. So in this animation over here, I have X as the fixed conductor, which, yeah, from your perspective is clockwise. All right. But what we're really paying attention to is what's happening with these B fields as they interact with this straight conductor. Because as you know, through the straight conductor on the right-hand side, the B fields are all pointing downwards. So your hands will all be pointing down. The dot tells you that your thumb must point towards your nose. Okay. And as a result, the force acting on that conductor will be pushing it towards the right. So that's what's going to happen here. The magnetic force will cause that red conductor to move towards the right. Now let's unfreeze the blue and freeze the red. Okay. So the blue will be the mobile conductor, and the red one will be the fixed one. Now, with the fixed conductor, this red one over here, I'm not going to draw all the circles for it, but you know that red means, according to right-hand rule number 1, that the thumb points to your nose, and the B fields are at least traveling downwards relative to where the blue conductor is. Okay, so the blue conductor sees nothing more than, they're not perfectly parallel, but at least from this perspective, it looks like relatively parallel B fields. So go ahead, orient your hands, top to bottom. Okay, because B fields always point from north to south. X means that your thumb must point into the page, and as a result, the conductor will move towards the left. Okay, so this conductor will move towards the left. All right, I just want you guys to be able to see this, and this does happen. All right, so once again, I have a current in this setup over here. I just have current that's going towards you on this black wire and returning from you through the white wire directly up above. I know that you can't see it from camera view, but what I did was I short-circuited over there, and maybe I should have demonstrated that afterwards, because this was working, and I don't know if it's going to work anymore now, but hey, we're doing it live, and I hope that I didn't damage that. So if all goes well and I push the button, you'll see that these two will repel each other. Sweet. There you have it. Physics at work. There's some smoke there. Now the fuse is popped, and that's it for today. Thank you guys for joining me, and I'll catch you guys in the next episode.